Hello, everyone. Thank you all for joining us today. Today's webinar is Create a Better Moisture Shield and Prevent Floor Failures and is presented by Evonik. Your presenter today is Shafiq Fazel. Shafiq Fazel is an applied technology manager at Evonik Corporation in the Crosslinkers business line. His current focus is developing new products, including polyura, high solids, and waterborne epoxy curing agents for coating applications. My name is Alex Payne with UL, and I'll be moderating today's webinar. Please send us your questions by typing them in the questions box located on your screen. Our panelists will answer them at the end of the presentation. We are also recording today's event and will send you a link by email when it has been posted to ulprospector.com. Now, I would like to turn the presentation over to Shafiq.
Thank you for the introduction, and hello, ladies and gentlemen. I really appreciate all of you taking time out of your busy schedules to listen to my presentation. As Alex mentioned, the topic I will be discussing today is Create a Better Moisture Shield and Prevent Floor Failures. The agenda of my talk, I will start out with an introduction and give examples of moisture-related floor failures, get into a couple of different moisture mitigation techniques and why use moisture vapor barriers, then get into the benefits of new curing agents from Evonik for moisture vapor barrier applications. I'll share some performance results, and then I'll finish off with a summary. So let's begin. So the question is, what problem are we trying to solve? In this case, it is moisture-related problems with floor coverings and coatings applied over concrete slabs. Again, it is concrete slabs and it's for mostly horizontal applications, so it's over the ground. And so if you search Google and type in moisture-related floor failures, you will get over 25 million hits. And that's because this is a real problem and it costs installers, building owners, applicators over hundreds of millions of dollars annually. And some examples of the floor failures I've listed here are blisters in coatings. Again, that is due to moisture vapor, again, coming from the concrete. Disbondment of tiles. So in this case here, where you have moisture vapor coming up and then degrading the adhesive under the tiles, again, causing the disbondment. The wet floors, and these cause, there are safety issues with that. And a significant issue also is mold and mildew growth, where moisture collects under the floor coverings. Again, over time, you have moisture, mildew, and mold problems, and that can affect the indoor air quality. So some of the examples I have listed here might seem trivial, but then it is actually a big problem because a lot of times the applicators have to remove the flooring system. So it's sometimes not just one coating. They might have to remove multiple layers. And then after removing it, they had to rebuild. So that's a significant cost right there. There could be a cost of remediation. And then, of course, there could be liability. So again, as I mentioned, it can be very costly. So now kind of get into, so I talked about the moisture-related floor failures, give you examples. So the question now is, where is this moisture source? So the moisture source, if you look at the schematic I have here, so what you have is usually concrete is placed on top of a soil. And then on top of the concrete, you have the floor coverings or coatings. And a lot of times these coatings or coverings are applied over concrete for either functional reasons to protect the concrete or for decorative reasons. And so one of the moisture source is from the ground or soil. So if you don't have any kind of protection here in terms of putting some kind of vapor retarder, the moisture vapor from the soil can come up right up to the surface. And then another source of moisture is concrete itself. So if you look at the concrete composition, generally you have, it's made up of different aggregates, cement, but then, water is added to the cement to cure the cement, but not all of that water is used up for the hydration process with the cement. So you have excess water, and then the fact that concrete tends to be porous, you kind of have moisture vapor that can kind of pretty much travel across in the concrete. So the next question is, what makes moisture vapor come up to the surface? So what are the drivers that get the moisture vapor from the ground to up to the surface? And one of the drivers is hydrostatic pressure. So this is the upward pressure when concrete is placed below ground. So this is a natural force that pretty much gets the moisture up to the surface. Another one, which is a more serious issue, is the osmotic pressure. And osmotic pressure can produce forces that are several orders of magnitude higher than the hydrostatic forces. So osmosis is defined as the spontaneous flow of liquid through a semi-permeable membrane from a dilute solution to a more concentrated solution. So for osmotic pressure to occur, you need three requirements. One is presence of moisture, and which I discussed before, presence of a semi-permeable membrane, and that is actually the concrete acts as a semi-permeable membrane. And then the final requirement is presence of salts or water-soluble organics. And if you have all these three conditions, so you have a chance of osmotic of pressures to occur. And if you look at the drawing picture below here, if you have potential osmotic pressure, and then if you do put a floor covering or a coating on top of that concrete, you pretty much that kind of force can either form blisters or disbondment of anything that you place above. So now talked about in terms of the moisture source. Now kind of get into the moisture mitigation technique. So what can you do about solving this problem? One of them is actually applying a moisture vapor permeable coating on top of the concrete. This allows the moisture vapor from the concrete or ground to diffuse through. So this is actually a very good technique where you have a high potential of osmotic pressure. So this coating actually acts as a relief valve. So pretty much it allows moisture to pass through. However, if you're using this kind of coating, then you need the subsequent layers that you put on top. So the floor coverings or coatings that you put on top has to be breathable as well, so the moisture can pass through. Another moisture mitigation technique is using a moisture vapor barrier. Actually, in this case, you're actually blocking the moisture vapor from coming up to the surface. And this is a very good technique when subsequent layers you put on top are non-breathable. And this is actually most commonly used because most of the coatings or coverings that you use, like seamless flooring, terrazzos, and if you have floor coverings like tiles, carpet, laminate, they tend to be non-breathable. So this is a more common way of, in terms of moisture mitigation technique. And this is where I will be focusing my talk. So now we're talking about moisture vapor barrier. So then the question comes out, okay, so we have to block the moisture vapor, but then how much do we need to block to be called a true moisture vapor barrier? So there was actually a standard practice established in 2013 for two-component resin-based membrane forming, moisture mitigation system. So this is for under resilient floor coverings, and that's the STM F3010. Generally, it kind of outlines different performances of these coatings that it needs to meet. But the main thing is that actually it specifies that moisture vapor permeance needs to be less than 0.1 perms as tested by ASTM E96. Another definition, actually there's one for from the International Residential Code for less than 0.1 perms, and that is defined as a class 1 moisture vapor retarder. So pretty much the goal here is to develop a moisture vapor barrier that can meet the less than 0.1 perms. So looking at in terms of the ASTM E96 testing in measuring the moisture vapor permeation, you can see again the schematic here. Basically you have a pan that's filled halfway with water, and then you are sealing this pan with the sample that is coated with the moisture vapor barrier. And what you're doing is to measure the moisture vapor transmission. You're actually looking at the mass loss, so how much of the moisture vapor that passes through. So you're looking at the mass loss over time and surface area of the sample. And that gives you the moisture vapor transmission. And from that, you can calculate the moisture vapor permeance by dividing the moisture vapor transmission by the vapor pressure differential across the sample. So this is how pretty much you are measuring the permeance. So this slide now outlines the approach that Evonik takes to drive new product innovations. The three key market trends focused to develop new products for moisture vapor barrier applications are enhanced performance, improved productivity, and environmental friendliness. So to start out with the enhanced performance, the key focus here is on improved adhesion. So these type of coatings are applied directly to concrete, so it needs to have a very good adhesion to concrete. Also, mechanical property is very important because not only is these type of moisture vapor barriers applied for residential type application, but also for industrial type applications. So it's those two are the key focus. Another one is actually improved productivity. This is very important for our customers because they do want fast cure at low temperatures. Overall, again, fast return to service. It allows for reduced downtime. So then again, our customers can finish the job quickly and then move on to another job. So again, it's all about productivity. And lastly, eco-friendly. And so the coatings that moisture vapor barrier you apply to concrete, not only does it have to be low VOC to protect the applicators, but then also low emissions. So you're protecting, in that case, the building occupants. So the technology that's used generally for these moisture vapor barrier application are thermoset epoxy coatings. Thermoset epoxy coatings is composed of the epoxy resin, which is generally a bisphenol A or bisphenol F diglycidyl ether. That's considered part A, and the part B is the curing agent or a hardener. Our focus here is on the curing agent side in terms of developing new curing agent. So if you look at the box here, in terms of what type of curing agents are currently used, generally right now you see it is composed of diamine, which is adducted, and a plasticizer. So an example here is like isoflurone that's adducted with a bisphenol A resin, and then you're adding the benzyl alcohol to help with not only just reduce the viscosity of the curing agent or hardener, but also increase the compatibility, because generally, you know, the liquid epoxy resin, the part A, is an aromatic material, so you need to have aromatic composition on the curing agent side to help with the compatibility. So those are the advantages. It helps in terms of these kind of systems have high conversion of epoxy amine reaction, gives you very good performance. However, the disadvantage is that, you know, since you're using these external plasticizers like benzyl alcohol, they do tend to emit out of the coatings over time. And since you have some of these emitting out of the coatings, it does leave some voids in the coatings, which then, again, create pathways for moisture vapor to pass through. So then that increases the moisture vapor transmission. So generally, these type of systems do not make for very good moisture vapor barrier application. So in that case, we develop new technology utilizing proprietary diamine, which is internally plasticized. So it requires low to no plasticizers. In this case, the advantage here is that you get the similar performance as a standard curing agent, but because there's no external plasticizers, there's you know, very low emissions and again, improved moisture vapor barrier properties. So now I'm going to start getting into the data and introduce the two new curing agents for moisture vapor barrier application. So these are the Ancamine 2739 and Ancamine 2800. And these are, again, solvent-free epoxy curing agent based on the new proprietary diamine technology, which I mentioned before. Again, these are built-in internal plasticizer, non-emissive technology. And I will, you know, be comparing them to a standard curing agent, which which have external plasticizer like benzyl alcohol at around 40% system. These are standard commercial curing agents. And CA1, so these are CA1 and CA2. CA1 being the more slower cure for ambient cure application. CA2 is a faster cure for cure down to lower temperatures. So if you look at the table here, you're basically comparing the handling properties of the two new curing agents, Ancamine 2739 and 2800, to CA1 and CA2. So the key takeaway, so I'm looking at the equivalent weights, gel times, viscosity, and mixed viscosity. And again, these were actually cured. So these are the curing agents. The resin side was the bisphenol A, bisphenol F blend, epoxy resin. Also, there was some monofunctional Epodil 748 material in the resin side. And the key takeaway here is that generally, even though these 2739 and 2800 do not have external plasticizer, what you can see is even then you still have very low viscosities and similar gel times as a standard curing agent. If you look at the cure speeds down, so these are designated as thin film set times, phase 3. You look at, in this case, what we have is Ancamine 2739 having similar cure speeds as CA1, and the faster curing Ancamine 2800 being more similar to CA2. Even though you can see a little faster cures with 2739 and 2800 versus their standard curing agent counterparts. This slide here is pretty much looking at the viscosity build over time. So when you mix the curing agent with the epoxy resin, what happens is you start, the viscosity starts increasing. And here again, it kind of follows the same trends as what in terms of cure times, which I mentioned in my previous slide. The 2739 and the CA1 are more slower cure. So you can see a viscosity build is a little slower, while 2800 and CA2 are faster. Faster cure, so the viscosity build is again faster, and that's kind of see the same trends, at lower temperature. So there's nothing really surprising till now. So now I'm gonna get into the shore D hardest build. So this is the hardest build after you mix the two components together. So this is where you now start seeing some differentiated results. Looking at 2739 versus the CA1 counterpart, what you can see is, and also 2800 versus CA2 counterpart, what you can see is both of these systems build hardness much faster. So within 16 hours, most of that hardness is already built in. And this is again at room temperature. And then if you look at lower temperatures, down to 10 degrees Celsius, same thing. You see 2739 much faster in terms of hardness development versus CA1, and 2800 much faster against CA2. So again, the key takeaway here is that you get much faster property development with these new curing agents that uses the proprietary diamines. Now get into the mechanical properties. So looking at this chart here is actually showing the compressive strength of the Ancamine 2739 and 2800 compared to CA1 and CA2. Again, here is what you see is significant improvement. It's almost 2 times improvement in compressive strength versus again CA1, CA2. But not only that, you also see almost 2 times increase in compressive strain versus CA1, CA2. So these systems, these new curing agents tend to be not only stronger, but a tougher material versus the standard curing agents. This chart here on the right actually shows the creep resistance. So creep is pretty much measuring deformation. Deformation of the material with a constant force. So you can see here, and over time. So what you see here is comparing Ancamine 2739 to CA2. So if you look at the CA2 material, what you see here is actually the material does deform over time upon load of 19 kilonewtons. Whilst 2739, what you see is a very slight deformation. Even 19 kilonewtons, and even at higher force, you do see a much slower, less deformation versus standard curing. And the picture below here kind of shows you can see that Ca2, that material after the test, you can see the deformation, while 2739, the sample kind of looks the same way as it did before the test was done. Now, kind of, so I kind of discussed a lot of the mechanical properties and harness development and handling properties. So now I'm going to focus on the moisture vapor barrier properties of the Ancamine 2739 and 2800. So this is starting point formulation that is for the moisture vapor barrier application. So what you see is on the resin side, you have a blend of the bisphenol A resin with a monofunctional diluent like Epodyl 748 and a difunctional diluent like Epodyl 749. And on the curing agent side, what you have is just a standard, again, same 2739 or Ancamine 2800. And some of the, in terms of mix ratios and the viscosity data is shown here below in the table. So again, this is specifically a formulation specifically developed for the moisture vapor barrier application. So now I'll talk about what's important for moisture vapor barrier application. As I mentioned earlier, an important performance is to have very good adhesion to concrete because it's applied directly to concrete. So what you see here in terms of Ancamine 2739 and 2800, they adhere really well to concrete, not only dry concrete, but damp concrete, where you have concrete that has 5 to 10% moisture, you still get very good adhesion. And then a more harsher test is actually adhesion to green concrete. And how we define green concrete is actually concrete that is cured less than 28 days. So below here kind of gives you a little bit more in-depth adhesion to green concrete. So these are adhesion on concrete, after 6 days, pour 10 days, 14 days, and 28 days. And you can see a consistent results with adhesion. So you get very good adhesion right even 6 days after the concrete is applied. And pretty much in terms of test method, these was the dolly pull testing, STM's D7234. And as you can see, all the adhesion, all the tests had a bulk concrete failures. So that means it had very good adhesion to concrete. The next slide here shows the carbamation resistance and intercoat adhesion. And this is, again, another important properties of a moisture vapor barrier, because this is, moisture vapor barriers, again, goes directly on concrete, but then you are going to come back, either apply either another coating or a floor covering. And for that to occur, you need that good adhesion, again, to the subsequent layers that you put on top. So what you see here is the initial table here is carbamation resistance. One of the properties for epoxy curing agents, epoxy coatings, is the carbamation. And a lot of times what happens is when you apply the coatings, the amine side, the hardener side, can actually react with the CO2 from the air and cause these kind of whitening on the surface. And what happens, it kind of leads to poor intercoat adhesion. So the data here is comparing 2739 to CA1. What you see is that, the 5 being really good, you see that you get very good carbamation resistance with these new curing agents. And then we actually did test the intercoat adhesion. So what we did was, take an aliphatic polyurea and applied it on top of 2739 and 2800 after 4 hours cure, and then after 24 hours cure. And the same thing we did with the cementitious overlay. A lot of times cementitious overlay is put on top of moisture vapor barrier before you come down with a floor covering like tiles or wood laminate floors. And so that was applied after 6 hours and then after 24 hours. And the data here, I'm not going to go in detail, but pretty much shows you get very good intercoat adhesion to the top coat. And then the picture on the bottom right kind of shows you, again, you have moisture vapor barrier 2739. You put a cementitious overlay, and by Dolly pull testing, you get a very good adhesion of the cementitious overlay to 2739. So now we're coming full circle to the moisture vapor transmission properties. So if you remember my earlier slide, I said that one of the key performance that we are targeting is for the moisture vapor barriers to meet the less than or equal to 0.1 per rating. Again, that was an important criteria. So what you see here on the table is, so what we have on the y-axis is actually moisture vapor transmission or permeation in perms. On the x-axis, we have the coating thickness in mils. And so generally what we have is, you need to, the red line shows that this is the boundary for meeting the 0.1 perms. We measured, and all these testing that we did was with the third-party independent lab. And what we see, a commercial moisture vapor barrier at 16 mils, just above the 0.1 perm target. With Ancamine 2739, what you can see is at 16 mils, you easily meet the 0.1 target. We only have one data point for 2739, but with 2800, we have 3 data points. So we actually went down to even 10 mils, 10 mils coating thickness. And what you see here is, even at 10 mils thickness, you do pass the 0.1 perms rating. So that pretty much means that you can apply 30 to 35% less material, and again, to meet the 0.1 perms, which is again significant cost and use savings for our customers. And finally, so this is my summary. Pretty much Ancamine 2739 and 2800 are excellent moisture vapor barrier choices. Ancamine 2739 has a low viscosity, excellent carbonation resistance, long pot life, very low emissions. Again, as I mentioned before, excellent adhesion to concrete. And then also it is a LEED version 4 compliant. A newer product is the Ancamine 2800. And that is actually a faster cure version of 2739. So it kind of has a similar properties to 2739, but it is a faster cure. So it can cure down to lower temperatures. And again, it kind of has a similar performance, excellent moisture vapor barrier properties, and excellent adhesion to concrete. So that concludes my talk, and I'll be happy to answer any questions that you might have.
Great. Shafiq, this is Alex. I will help you with the question and answer session. So our listeners, if you have any questions for our presenter, please find the questions box on the GoToWebinar panel and type them in so that we can start answering. We do have our first question, and it's from Susan, that asks, does the concrete need to be shot blasted or grinded before applying the moisture vapor barrier?
Yes, actually. We recommend that the concrete is shot blasted to a profile of CSP3. And CSP3 is basically like again, light shot blasting as defined by the International Concrete Repair Institute. So that actually does allow for improved adhesion of the moisture vapor barrier to the concrete.
Great, thank you. Our next one comes from Jeff, and it says, besides cure speed, are there any other performance differences between the two Ancamine products, 2739 and 2800?
Actually, as I mentioned, they're very similar in terms of performance-wise, moisture vapor barrier performance. I would say maybe 2800 is a little better. As I mentioned, if from the last slide, you get down to 10 mils and still pass the perm rating. Otherwise, in terms of adhesion and other properties, very similar. The only difference, major difference, is the cure speed. So, again, with the 2800, it's a faster cure, 5 to 6 hours versus 5 to 6 hours cure times versus 2739. It's about more like 9-10 hours cure time.
Great. And then another question from Mario asks if both of those products are VOC free.
Yes. So again, sometimes depends how you define VOCs. A lot of times, again, it's different region to region. How Europe defines VOC versus North America is a little different. But generally, what we say, these are VOC free. VOC free. So if you define like benzyl alcohol and other plasticizer, in terms of very low to no VOCs in the product.
Okay, great. Our next question is from Jessica, and she asks, do you see the market trending away from epoxy moisture mitigation systems towards water-based systems? And if they meet the less than 0.1/10 perm criteria?
So this is something actually we're kind of looking into this in terms of water-based system. Right now, in terms of generally what we still see is these solvent-free systems, because solvent-free, a lot of times to meet this criteria of 0.1 perms, you had to apply film thickness, generally at least above 10 mils to get that to pass this test. And a lot of times the waterborne systems, because you have water in the system, you cannot apply very thick films. So generally, if you might be able to do it, but then you would have to apply multiple coats. So you might have to apply 2 to 3 coats to get to the perm rating of a solvent-free. But it's something that we're trying to see coming up with new technology that we can apply thinner films and still pass the 0.1 perm rating.
Okay, great. Next question is from Lorenzo, and he asks, how do you control viscosity increase?
So viscosity increase a lot. So this is a viscosity increase from mixing part A and part B. That's what I'm assuming. That's the question. And generally, you cannot control it except as soon as you mix the two together, they will start reacting. So these are thermoset systems. So if somebody wants a slower cure, wants more slower reacting system, so you have more time to work with the material, then we would recommend Ancamine 2739. Again, it's a longer working time, it's a little slower, but then again, in terms of cure speed, this is slower. For those who kind of don't mind the fastest cure speeds, then 2800 is what we would recommend.
Great, and I show that we have a couple more questions. So if you guys have any further questions that you would like to get to today on the call, please shoot them over right now. So the next couple questions I will ask if the products are available in Europe and are samples available.
Actually, from what I understand, Ancamine 2739 is available in Europe. I'll have to check with Ancamine 2800, but in North America, both products are commercial and available.
Thank you, Shafiq. That wraps up our questions and all the questions we have today on the call. If anybody has any further questions, we will provide Shafiq's contact information and means to reach to him directly for any further questions that anyone may have. I want to thank everyone for attending today's webinar. Just as a reminder, we will send you an email with the link to the recording of the webinar, and so you may watch it again anytime and share it with others at your company. Thank you again for attending, and everyone have a great day.